In problem 1 of homework 9, we want to test whether the mean year-end bonus for a given company is different from the reported value of 125,500. In part A, we have to determine the null and alternative hypotheses. Now, because the null hypothesis always includes equals, the phrase highlighted in blue is the alternative hypothesis. So the population mean, mu, which cannot be known but can be estimated. The alternative hypothesis is saying that mean is not equal to 125,500. Now, since the null hypothesis is the opposite of the alternative hypothesis, then we say the null hypothesis is mu equal to 125,500. Now, our significance level is 1% or 0.01. We're going to determine the critical values for this test. The point estimate, the standard error, and the value of the test statistic. And we're going to do all this stuff in Excel. The sample size is 40. The sample mean is 127,660. And the population standard deviation is 25,730. And then the significance level is 1%. These values have been pasted into this Excel spreadsheet. The sample mean, the population standard deviation, sigma, the sample size, and a significance level of 1%. Now, since this is the population standard deviation, the population variance is the square of the population standard deviation. Down here, where we want to find the standard error of the mean, we first have to calculate the variance of the sample mean. The variance of the sample mean is not the same thing as the variance of the variable. The variance of the variable is quite large. The variance of the sample mean is always smaller than that value. But you just take the variance of the underlying variable and divide it by the sample size. The standard deviation of the sample mean, also known as the standard error of the sample mean, is just the square root of the thing we just calculated, the variance of the sample mean. Now, the null hypothesis indicates that this is a two-tailed test. So we have to divide the alpha, or significance level, by 2. So the area in the upper tail is going to be 0.005. And the area in the lower tail is going to be 0.005. Now in part B, we want the critical values at 3 decimal places. We can get the Z critical values from the standard normal table, or we can get the Z critical values from the infinity row of the t-distribution table. Now we're going to get Z values because this is a sigma known problem. When sigma is known, you use Z. When sigma is unknown, you use T. So with an upper tail value of 0.005, which is just equal to alpha divided by 2, we scroll down until we get to the infinity row of the t-distribution table. And in the infinity row and column 0.05 of the t-distribution table, Z is equal to 2.576. Our critical values are plus or minus 2.576. Next, we want to find the point estimate of the difference between the population mean and its hypothesized value. The hypothesized value is from the problem, 125,500. We're going to copy that and use that in Excel. So we have the difference between the point estimate and the hypothesized value of 125,500, which is $2,160. The test statistic is just the ratio of this point estimate of the difference divided by the standard error. So the test statistic to 3 decimal places is 0.531. In part B, we need to enter the critical values. The critical values were plus or minus 2.576. The point estimate of the population mean is given in the problem. Now, I don't want to include a comma here. I'm going to just enter it as a number because sometimes Cengage now is okay with commas and sometimes it's not. The point estimate, the difference between the population mean and its hypothesized value was equal to 2,160. And both these numbers are to 0 decimal places. The standard error we computed at 4,068.27, and we need that to 2 decimal places, so I'm going to delete 1 0. The test statistic needs to be to 4 decimal places. So we go back to Excel, increase the number of decimal places to 4. With a test statistic equal to 0.5309, we copy that in. If the test statistic is in between the 2 critical values, which is the case here, then we say the difference, this difference here, is insignificant. And what we're doing is we're basically concluding that the null hypothesis is perhaps correct. However, we cannot accept a null hypothesis. So we can reject it or not reject it. So can you reject the null hypothesis? No. The reason why we can't accept the null hypothesis is because by saying that you cannot reject the null, that kind of helps you avoid making a type 2 error. Now, since the null hypothesis cannot be rejected, then we cannot say the population mean is not equal to 125,500. If we had rejected the null hypothesis, then we could have said that the alternative hypothesis is true. However, we could not reject the null hypothesis. So then we cannot say that the alternative hypothesis is true. So, thus, we cannot conclude that the year-end bonuses paid by Jones and Ryan were different from that of Wall Street security firms. And if I check my work, I should get all green check marks. So what is the conclusion of this test in layman's terms? The test results indicate that the difference in the year-end bonuses that Jones and Ryan paid to their employees and those of Wall Street securities firms is insignificant. In other words, there's no difference.